In 1985, two new personal computers arrived with a similarity that made their differences almost impossible to ignore. Atari's 520 ST, introduced at the Winter Consumer Electronics Show in January, was built around Motorola's 68,000 processor and entered the market with an aggressive price that immediately made 16-bit computing look more accessible. Months later, Commodore unveiled the Amiga 1000. It also used the Motorola 68,000, yet the machine appeared capable of visual and audio behavior that could not be explained by the processor specification alone. The Amiga cost considerably more, $1,295 without a monitor, but Commodore was presenting something more elaborate than a faster version of the same idea. Its demonstrations showed color graphics, animation, multiple screen modes, sampled sound, and multitasking in combinations that were unusual for a personal computer of the period. Atari's machine had reached the public first and offered its own compelling argument: a fast 68,000 system, graphical desktop environment, substantial memory, and a price low enough to put pressure on every competing 16-bit computer. On paper, the rivalry might have looked straightforward. The two machines emerged from the same processor generation. At the heart of each system was Motorola's 68,000 CPU family. Their broader ambition was also shared: to push home and personal computing beyond the limitations that had defined the earlier 8-bit era. Yet watching them work exposed a deeper difference. The 68,000 was only one participant in what the computer could do. A processor could execute instructions rapidly, but graphics still had to be generated, memory moved, sound produced, displays synchronized, and peripheral activity coordinated. The way engineers divided those jobs determined how much work remained for the CPU and what kinds of software could be produced efficiently. Atari and Commodore had arrived at very different answers. The ST placed the 68,000 at the center of a comparatively direct and economical system intended to reach the market quickly. The Amiga surrounded its processor with hardware designed to take responsibility for certain demanding tasks before the CPU ever had to perform them itself. None of that guaranteed commercial victory. Specialized hardware could increase cost and complexity. A simpler machine could reach buyers earlier, attract developers sooner, and succeed in applications where elaborate multimedia circuitry offered little advantage. In 1985, those consequences were still unfolding. What was already clear was that comparing the two computers by CPU alone missed the most important part of their design. To understand why the Amiga behaved the way it did, the story had to move backward before Commodore owned the machine and before the Amiga name appeared on a finished computer, to an engineer who had already spent years questioning how much work a central processor should be forced to do. His name was J. Miner. J. Miner's instinct to divide work across specialized hardware did not begin with the Amiga. Years earlier at Atari, he had already been working in an environment where general-purpose processors were too limited to handle every real-time task efficiently. The Atari Video Computer System, later known as the 2600, had forced engineers to confront that problem directly. Its inexpensive processor could not generate an entire television display by itself while also running the game. Atari therefore relied on custom circuitry to handle timing, graphics, and sound functions that had to occur at precisely controlled moments. Miner was deeply involved in that hardware work, and the experience established an important engineering lesson. When a task is repetitive, timing-sensitive, and predictable, dedicated hardware can perform it more effectively than asking the central processor to do everything in software. That principle became even more visible when Atari began designing the machines that would become the 400 and 800. The new computers needed to do more than play cartridge games. Atari wanted them to support home computer graphics, programming, and applications, while retaining the visual strengths that had helped define its game systems. Miner served as system architect with engineers including Joe Deckwer and others, and the design divided responsibilities among several chips. The 6502 remained the general-purpose processor, but display work was handled through specialized hardware. Antic processed display instructions and coordinated the way screen data was fetched from memory. CTIA, later replaced by GTIA, converted that information into the graphics that appeared on the television or monitor. Pokey handled sound as well as several input and communication functions. The result was not a single CPU surrounded by passive support logic. It was a machine in which different pieces of silicon had distinct jobs. Antic was especially revealing because it could process display lists independently enough to reduce the amount of constant intervention required from the 6502. That allowed programmers to construct screens from different display modes, perform scrolling, and create effects that would have demanded much more processor attention on a simpler system. The architecture still had limits, and Miner did not design every component personally. Atari's 8-bit machines were the work of a team, and their custom chips reflected contributions from several engineers. What mattered for the later Amiga story was the pattern Miner had helped refine. Graphics performance did not have to depend entirely on increasing CPU speed. A computer could become more capable by deciding in advance which jobs deserved their own hardware. That idea would remain with Miner after his Atari years, but the next machine he wanted to build would push it far beyond display lists and game-oriented graphics. By the early 1980s, the possibility of a 16-bit system built around a far more powerful processor was opening new territory. Miner did not simply want a faster version of the computers he had already helped create. He wanted a machine in which specialized hardware could work beside a new generation of CPU from the beginning, with graphics, sound, and data movement treated as fundamental parts of the architecture rather than secondary features added later. That opportunity would emerge through a small company and a project with a code name that, for a time, existed more securely as an engineering ambition than as a business: Lorraine. Lorraine began as an attempt to turn that philosophy into an entire 16-bit system. The company behind it had started as High Toro before adopting the Amiga name, and its early business was not yet centered entirely on selling a finished computer. The team explored game-related products and peripherals, while the larger machine developed in the background, partly because designing custom silicon demanded more money and time than a small startup could easily absorb. Miner's ambition for Lorraine went well beyond attaching a new processor to conventional display hardware. The Motorola 68000 would provide the general-purpose computing power, but much of the machine's identity was being designed into custom chips responsible for graphics, sound, memory movement, and display coordination. Building that architecture required several difficult projects to advance together. The silicon had to be designed and verified. Prototype hardware had to prove that the chips could cooperate. An operating system and development environment had to be created around hardware, unlike the conventional personal computers already on the market. Software demonstrations had to show potential investors and partners why the complexity was worthwhile before the company had the resources to manufacture a polished machine. By January 1984, Amiga was demonstrating Lorraine privately at the Consumer Electronics Show in Las Vegas. The prototype was still far from a commercial desktop computer. Its custom chip functions were represented by elaborate prototype hardware, and parts of the operating system remained unfinished. So engineers created demonstrations designed to expose what the architecture could already do. The most famous showed a large red and white checkered ball rotating and bouncing across the screen with a shadow beneath it, accompanied by sampled sound. The demonstration was visually memorable, but behind it was a more serious problem. Amiga was spending money faster than a small independent company could comfortably sustain. Custom chips could not be brought to market through engineering enthusiasm alone. During this period, Amiga entered a financing agreement with the Warner-owned Atari Inc., receiving badly needed funding while granting Atari contractual rights tied to the Lorraine technology if Amiga failed to meet its obligations. The arrangement gave the company time, but it also placed the future of Lorraine under severe pressure. By 1984, the machine was no longer merely an ambitious engineering project searching for a market. Its ownership and the survival of the technology itself were becoming part of the story. Commodore then entered the negotiations. Rather than acquiring only limited rights to the chipset, Commodore ultimately purchased Amiga Corporation in 1984, bringing the engineering group and Lorraine project under a company with far greater manufacturing and distribution resources. The acquisition did not instantly transform the prototype into a finished product. The custom silicon still had to be completed, the operating system had to mature, and the elaborate prototype architecture had to become a computer that could be built repeatedly, shipped, supported, and sold. Yet the most immediate danger had changed. Lorraine had survived the startup's financial crisis and gained the backing of one of the largest home computer manufacturers in the world. That survival also intensified the stakes, because while Commodore's new Amiga team worked to convert its unusual architecture into a commercial system, another 68,000 computer was moving toward market under the Atari name. Before those machines could compete, however, the technology that made the Amiga so unusual had to be reduced from an ambitious collection of ideas into a working division of labor between the 68,000 and 3 pieces of custom silicon. Those 3 chips did not replace the 68,000. They changed what the 68,000 had to spend its time doing. At the center of the arrangement was Agnus, the component responsible for much of the Amiga's direct memory access and for coordinating several operations that could reach chip memory without requiring the CPU to move every word itself. That ability mattered because graphics and sound consume streams of data. On a simpler machine, the central processor often has to participate directly in transferring or transforming much of that information. The Amiga instead gave selected tasks their own routes to memory. Agnus also contained 2 of the architecture's most distinctive engines. The Blitter was designed to move and combine rectangular blocks of data, operations that appeared constantly in graphical software. It could copy image regions, apply logical combinations, fill areas, and assist with line drawing, while the 68,000 was available for other work. The significance was not that the CPU became unnecessary. The Blitter accelerated a specific family of repetitive memory operations that otherwise consumed processor time. Beside it sat the Copper, a far smaller and stranger kind of coprocessor. The Copper executed a limited instruction stream synchronized with the position of the video beam. It could wait for a particular point during screen generation and then alter selected hardware registers. That allowed software to change display parameters within a single frame, rather than treating the entire screen as one fixed configuration. Color registers could be modified partway down the display, pointers adjusted, and visual effects coordinated with the raster without forcing the 68,000 to supervise every precisely timed change. The Copper was not a second general-purpose processor. Its power came from being extremely specialized. Denise handled the final stages of much of the display system. Bitplane data fetched from memory could be interpreted into screen pixels, color information passed through the video circuitry, and hardware sprites combined with the play field. Instead of storing each pixel as one complete color value, the Amiga commonly organized graphics into bitplanes, separate layers of bits, whose combination selected the displayed color. That organization gave the hardware unusual flexibility, although exploiting it efficiently required programmers to understand how the display machinery worked. Paula completed the original trio with another set of specialized responsibilities. Its most famous function was audio. Sample data could be transferred from memory through DMA and converted into sound across independent hardware channels, allowing the system to reproduce recorded waveforms without asking the 68,000 to generate every sample in software. Paula also handled functions associated with the floppy disk, serial communication, and interrupts. The result was not a collection of decorative chips surrounding a conventional computer. Graphics movement, display timing, sampled audio, and several data transfer jobs could proceed with substantial independence from the CPU. That gave software designers opportunities that would have been expensive in processor time on a more conventional architecture. It also created a limitation that demonstrations could hide. The custom chips in the 68,000 were not operating in separate universes. They competed for access to the same chip memory, and heavy DMA activity consumed memory cycles that the processor might otherwise use. A poorly planned display or aggressive combination of graphics and audio operations could therefore reduce the resources available elsewhere. The hardware rewarded programmers who understood when each engine needed the bus and how to arrange data around those demands. Amiga's sophistication was real, but it was a coordinated system rather than a source of unlimited free performance. By the time Commodore prepared that architecture for market, another team had already approached the same Motorola processor from almost the opposite direction: build the surrounding machine more simply, finish it faster, and make the price difficult to ignore. The Atari ST emerged from a very different set of pressures. After leaving Commodore and acquiring Atari's consumer operations from Warner in 1984, Jack Tramiel wanted a new computer that could restore the company quickly, compete with emerging 16-bit systems, and reach buyers at a price aggressive enough to make performance itself part of the value proposition. The engineering effort led by Shiraz Shivji therefore worked under an unusually compressed schedule. Atari did not have the luxury of spending years developing a multimedia architecture as elaborate as Lorraine. The machine still needed custom silicon, but those chips were organized around a more direct system design. The Motorola 68,000 remained the center of computation. The shifter converted display data from memory into the video signal. The MMU helped coordinate memory access, and Glue handled timing and several system control functions that tied the major components together. Other support hardware dealt with disk transfers and peripherals. These were genuine custom components, not passive pieces surrounding an otherwise generic computer. But they did not divide graphics and sound work into the same collection of specialized engines found in the Amiga. The ST's display system was more closely tied to a frame buffer in memory. Software that wanted to change large areas of the screen generally depended heavily on the 68,000 to manipulate that data. There was no equivalent in the original ST to the Amiga's Blitter for accelerating block graphics operations, nor a Copper independently changing display registers in synchronization with the raster. That difference was not necessarily a design failure. It reflected the priorities shaping the machine. A comparatively straightforward architecture could be completed more quickly, manufactured economically, and understood without requiring programmers to coordinate several multimedia coprocessors. Atari paired the hardware with TOS and Digital Research's GEM graphical environment, giving users a mouse-driven desktop at a time when graphical interfaces were becoming increasingly important to personal computing. The machine also carried a feature whose importance would become much larger than its cost suggested. MIDI input and output ports were built directly into the system. In January 1985, Atari showed the ST at the Winter Consumer Electronics Show, months before Commodore formally introduced the Amiga 1000. The 520 ST was promoted around the idea of power without the price, and its positioning made the strategic difference difficult to miss. Atari was not trying to reproduce every advanced multimedia capability that Amiga's engineers had spent years developing. It was trying to put a fast 68,000 computer with substantial memory, a graphical desktop, useful expansion connections, and a competitive price into the hands of buyers before rivals could establish themselves. That earlier arrival mattered. Developers could begin experimenting with the platform, dealers could show it, and consumers could judge a 16-bit machine they could actually purchase rather than one still approaching launch. When the Amiga 1000 finally appeared later that year, the confrontation therefore involved more than graphics circuitry. Commodore was asking buyers to pay for an architecture whose advantages came from specialized hardware working around the CPU. Atari had already placed a less elaborate but capable 68,000 machine in the market at a lower price. The next question could no longer be answered by examining block diagrams. It would be answered on the screen, where the architectural decisions inside both machines became visible in the software they could run. The difference became obvious once software turned the Amiga's architecture into motion. Scrolling backgrounds could move smoothly, graphical objects could cross the display without forcing every visual element to be rebuilt in the same way, and selected areas of the screen could change independently as developers combined the machine's display features with careful memory organization. The result was not merely prettier static images, it was a visual environment that encouraged movement, layered effects, rapid animation, unusual color transitions, and displays that could change character within a single frame. Some of the most striking demonstrations exploited that flexibility directly. Colors could shift as the screen was being drawn, different regions could use different visual treatments, and animated elements could appear to move with a fluidity that made the machine immediately distinctive in demonstrations, games, and creative software. None of these capabilities guaranteed good software. Developers still had to organize graphics carefully, manage memory bandwidth, and understand the limits of the display system. The Amiga rewarded programmers who learned how its visual resources interacted rather than treating the machine as a conventional computer with a more colorful screen. The Atari ST offered a different programming experience. Its graphics system presented developers with a more direct relationship between the frame buffer and the processor. When software wanted to redraw large portions of the display, scroll data, or move graphical objects, efficient 68,000 code and careful memory handling became especially important. That placed greater pressure on software technique, but it also made the system straightforward for many conventional applications. A programmer manipulating icons, windows, text, diagrams, or relatively static screens did not necessarily need the elaborate display techniques that made the Amiga so distinctive. The ST's high-resolution monochrome mode, in particular, helped make it attractive for productivity and professional software where clarity and desktop space mattered more than animated color effects. Game programmers and demo coders encountered the architectural difference more directly. On the ST, impressive animation increasingly came from discovering how efficiently screen data could be manipulated, exploiting precise timing, reorganizing memory, and developing software techniques that pushed the display beyond ordinary expectations. Amiga programmers approached many of the same visual ambitions through the possibilities already built into the display architecture. The contrast helped shape programming cultures around both machines. Amiga developers explored combinations of scrolling, sprites, color changes, animation, and display timing. ST programmers became known for extracting visual results that the machine's comparatively direct architecture did not obviously promise. As software matured, the comparison therefore became less useful as a simple list of colors or resolutions. What users actually saw depended on how effectively developers understood the particular machine in front of them. By the late 1980s, games, demonstrations, painting programs, and animation packages were making those differences increasingly visible. Yet graphics were only half of the multimedia argument. The next divergence could not be seen at all, it could be heard. The difference in sound exposed another way the two machines had divided work, and this time the rivalry produced a less predictable result. The Amiga's audio hardware was designed around sampled sound rather than relying only on simple tone generation. Paula could fetch digital audio data from memory through DMA and play several independent sample streams with little continuous intervention from the 68,000. For game developers and musicians, that meant recorded drums, voices, effects, and instruments could be reproduced directly from stored waveforms instead of being approximated entirely through a programmable sound generator. The importance of that capability became clearer as software began using it creatively. Games could combine music and effects with a character that felt different from the electronic tones associated with many earlier home computers. Tracker software turned relatively small collections of samples into complete compositions, and the machine's ability to replay digitized sounds helped make music production, demos, and multimedia a natural extension of the same architecture already supporting animated graphics. The processor still had work to do. Samples consumed memory, higher quality playback demanded more data, and sophisticated software could push the available channels beyond what the basic hardware provided directly. Yet, sampled audio was not being treated as an afterthought. It was part of the system's original division of labor. The Atari ST began from a different internal audio foundation. Its programmable sound generator was well suited to synthesize tones, noise, and conventional computer sound effects, but it did not provide the same native sampled audio machinery that gave the Amiga its characteristic sound. Software could still reproduce digital samples by using processor time and clever programming techniques, and developers eventually pushed the machine far beyond the apparent limits of its basic sound hardware. That ingenuity mattered, but it did not erase the architectural difference. If the contest had ended at internal audio capability, the Amiga would have held the more obvious advantage. The ST, however, had arrived with two ports that changed the comparison completely. MIDI input and output were built into the computer as standard features. For musicians already using synthesizers, drum machines, and other electronic instruments, those connectors could matter more than the character of the computer's own sound chip. Sequencing software could use the ST as the control center of an external studio, sending precise performance data to instruments whose sound generation happened outside the computer. That role became one of the platform's most durable strengths. Programs such as Cubase and Notator helped establish the ST in professional and semi-professional music environments, where stability, timing, software support, and direct MIDI connectivity created a practical ecosystem that internal audio specifications alone could not predict. The rivalry had therefore produced an important reversal. The Amiga's specialized audio hardware made the computer itself a capable source of sampled sound. The Atari ST became valuable to many musicians because it could coordinate equipment far more sophisticated than anything inside its case. Neither advantage canceled the other. They answered different needs, and by the late 1980s, those needs were helping separate the platforms into distinct creative communities. The contest was no longer simply about which machine could generate the more impressive demonstration. It was becoming a question of which complete system gave developers and users the strongest reason to build their work around it. The answer increasingly depended on economics rather than architecture alone. The Amiga 1000 had demonstrated what Commodore's new platform could do, but its launch position placed that capability behind a relatively high entry cost. The machine was impressive enough to attract attention from developers, artists, and enthusiasts, yet broad home computer adoption required more than technical admiration. Buyers compared complete systems, not engineering philosophy. They considered price, available software, dealer support, peripherals, and whether a platform seemed likely to survive long enough to justify the investment. Atari had already created an advantage by reaching the market earlier with a less expensive 68,000 machine. That head start gave the ST time to accumulate users and developers, while Commodore was still working out how to turn the Amiga from a premium showcase into a mass-market product. The relationship between price and software became increasingly important. A larger installed base gave publishers more reason to support a machine. More software made the platform more attractive to new buyers. That feedback loop did not guarantee permanent success, but it could magnify an early commercial advantage. Commodore eventually responded by changing the form in which the Amiga reached consumers. The Amiga 500, introduced in 1987, brought the same broad, custom chip philosophy into a far more affordable package, aimed directly at the home market. It was smaller, cheaper, and easier to position against other popular personal computers. The effect was more important than a simple price cut. The architecture that had looked expensive and exotic in the Amiga 1000 could now reach households and schools, game players, and young programmers in much greater numbers. That expanded the potential audience for software designed specifically around the platform. Atari, however, was not standing still. The ST family continued to evolve through additional models, memory configurations, and regional variations, while the platform developed a particularly strong presence in Europe. Its relatively straightforward 68,000 environment, existing software base, competitive pricing, and usefulness in areas ranging from productivity to music gave buyers practical reasons to remain within the ecosystem. The rivalry, therefore, entered a new phase in which neither machine could be judged only by the elegance of its motherboard. Developers had to decide where their software would sell. Retailers had to decide which systems deserved shelf space. Consumers had to weigh technical capability against the size and maturity of the platform around it. A feature that looked decisive in a demonstration could matter less than the availability of the applications someone actually wanted to run. By the late 1980s, the contest between Amiga and Atari ST had become a struggle between complete ecosystems shaped by very different paths into the market. The custom chip architecture still mattered, and so did the ST's earlier price and timing advantages, but those factors now expressed themselves through communities, software libraries, and expectations. The next stage of the rivalry would reveal just how differently those communities were beginning to use the two machines. By the end of the 1980s, those communities were giving the Amiga and Atari ST identities that no specification sheet could fully explain. On the Amiga, games, animation, graphics, software, sampled music, and the emerging demo scene increasingly revealed what developers could achieve when they treated the machine as more than a conventional 68,000 system. Deluxe Paint became one of the platform's defining creative applications, not because it transformed the Amiga into a professional graphics workstation by itself, but because it placed the machine's color and animation capabilities directly in the hands of artists, game developers, and hobbyists. Its influence spread beyond pictures made for display on the Amiga. Pixel artists used it to create assets for commercial games, and its workflow became closely associated with the visual language of late 1980s and early 1990s computer graphics. In games, developers combined motion, color, sampled sound, and screen effects into experiences that gave the platform a recognizable identity. The demo scene pushed that tendency even further. Programmers deliberately searched for undocumented timing relationships, unusual display combinations, and ways to coordinate the machine more tightly than ordinary software required. Technical limitations became material for competition. A screen effect that appeared impossible under normal assumptions could become the centerpiece of a demonstration precisely because another programmer might understand how difficult it was to achieve. The Atari ST developed a different reputation without being confined to a single market. It had a large games library, a strong European user base, graphics and publishing applications, and programmers who learned to push its hardware far beyond early expectations. Yet its most distinctive professional identity grew around music. Built-in MIDI, combined with increasingly sophisticated sequencing software, made the ST a familiar presence in studios where the computer's role was to organize complex arrangements of external synthesizers and instruments. Packages such as Steinberg's Cubase and C-Lab's Notator turned the machine into a serious production tool. Elsewhere, its high-resolution monochrome display and relatively clean desktop environment helped support productivity, programming, notation, and publishing work. These reputations were tendencies rather than boundaries. Amigas gradually found their way into music studios and audio production environments. Atari STs became especially visible through games and demo software. Those boundaries soon blurred as artists, programmers, businesses, and hobbyists explored both platforms in ways that often crossed their original purposes. What changed was the expectation surrounding each platform. The Amiga became closely associated with audiovisual creativity, while the ST built durable value through software, peripherals, productivity, and an unusually effective connection to professional music equipment. By then, asking which machine was better had become less meaningful than asking what a particular user intended to do with it. The rivalry had fragmented into several overlapping contests, each with different criteria for success. That diversity also concealed a problem both platforms were approaching. Their strongest characteristics were embedded in hardware, designed around assumptions made years earlier. Processor performance was rising, memory requirements were growing, display expectations were changing, and new computers were beginning to redefine what users considered normal. The next challenge would not be whether Amiga or Atari programmers could extract more from the machines they already understood. It would be whether either architecture could keep evolving fast enough as personal computing moved beyond the technological conditions of 1985. Return to 1985, when the Atari ST and Amiga appeared to belong to the same generation because both were built around Motorola's 68,000. That similarity had always been incomplete. What ultimately separated the machines was not a single benchmark or one dramatic hardware feature, but the collection of architectural decisions that determined how each system could develop once software, users, and markets began pushing against its original design. J. Miner's Amiga embodied an unusually ambitious commitment to specialized hardware at a time when personal computers still operated under severe limits of processor speed and memory bandwidth. That decision gave the platform capabilities that developers could exploit in ways few competing home computers of the period matched as naturally. It also meant that part of the machine's future depended on circuitry, whose fundamental responsibilities had been fixed during the design process. As expectations changed, Commodore extended the platform through later chipsets, larger memory configurations, faster processors, and new models. But the industry around it was moving rapidly as well. Display standards advanced, software became more demanding, and increasingly powerful general-purpose processors reduced the cost of performing work that had once demanded dedicated hardware. The ST encountered the same passage of time from a different starting point. Later, machines added capabilities absent from the earliest models, including Blitter hardware and the broader enhancements of the STE generation, as Atari tried to extend the usefulness of an architecture created under the intense market conditions of 1984 and 1985. Neither evolution produces a clean verdict on the rivalry. The Amiga's architectural sophistication did not guarantee that every market would value its strengths equally, and the ST's success in particular fields did not prove that specialized multimedia hardware was unnecessary. What the rivalry exposed more clearly was a recurring engineering problem, deciding which capabilities belong in flexible software and which deserve dedicated silicon. That question outlived both platforms. Modern computers routinely divide work among general-purpose CPUs, graphics processors, media engines, display controllers, audio hardware, and other specialized accelerators. The comparison should not be mistaken for a simple line of descent from the Amiga to modern GPUs, nor does it make the ST an evolutionary dead end. The significance lies in the architectural choice itself. Personal computers were becoming systems whose character depended increasingly on how work was distributed among different kinds of hardware, not merely on the headline processor inside the case.